Thank you, Kevin, and thank you for inviting me back. Tonight I'm going to talk to you about IoT on Raspberry Pi. Who has a Raspberry Pi here? Yeah, okay. I suspected lots of people would. Who's actually used it and it's not still in the box? Oh, few number, yeah. There's actually a help group on Reddit you can join for people who've bought them but not actually used them for counselling purposes. So IoT is Internet of Things, basically devices that sit on the internet but have capabilities into the outside world, like my prototyping board here. My name's John Staveley, I'm a Microsoft MVP. I'm Cark from Leeds and I run Leeds Sharp and IoT North, which covers everywhere from London to Scotland. My day job is C#, MVC, SQL Server, Angular, Azure, and a bit of IoT. I've got a couple of ongoing projects in that. I've used a lot of microcontrollers in the past, but I am by no means an electronics expert. So what I'm going to convey to you tonight is some of the how to make the electronics part of thing a bit easier and a bit more understandable. It's all going to be done in C#, so we're going to be going over how we set up C# on a Raspberry Pi, and how we set up .NET 5 on a Raspberry Pi, and how you then control the things. So there's a couple of interfacing standards you need to know a little bit about. So GPIO, which is switching things on or off, or receiving data on or off. PWM, which is sort of an analog output, and I2C, which is control all the things. And then once you've got your board, you need to talk to it, get it on the internet and talk to it, send it commands so you can get it to do stuff and also receive data back. So we use something called Azure IoT Hub to enable that, receiving updates back. So broadly speaking, this is a Raspberry Pi. So you've got a couple of USB 2 ports, USB 3 networking. It's also got a Wi-Fi chip there. This is for the camera, so you can attach the camera there. This is audio-visual connector, 2 micro HDMI ports, a USB 3 connector, and a display port. And the important stuff, which mostly what we're going to talk about, is the GPIO pins here and all the kind of things you can do with them. That's a 4B, so it's the 4th iteration. Raspberry Pi Foundation have got another £27 million worth of funding to develop the next model. So this is a form factor that's not going anywhere. You know, you can see it continue to evolve. Covered all that. And the thing you can't see is hidden under there is a micro SD card, and that contains the operating system. There are other ways of doing .NET on embedded devices. There's something called Meadow, where you can do it natively, and a Nano framework on, for instance, the ESP32. I don't know anything about these things, don't ask me questions. So one of the important things is, particularly when you're setting up, is you need a decent power supply. So the USB-C power supply you use your phone is not going to do the business here because it won't run a monitor of this size. You need something that's going to deliver at least 3 amps. You need something called the Noobs software, so you can go to Pimeroni, for instance, and they can send you a micro SD card with the Noobs software installed. That's basically a Linux Raspbian operating system already installed on it. Occasionally you need, like tonight when I was setting up, I needed a screen, keyboard and mouse. The only reason you need that is you can get it on the Wi-Fi. Once it's on the Wi-Fi, you can do everything remotely. You can VNC like onto a desktop on it, and so you don't need any of those things. And it just helps to have a fixed IP address for the Wi-Fi, so when you're at home, it doesn't keep, your VNC can just be pegged and your FTP can be pegged to that IP address, so it makes it a lot handier. There are lots of getting started with Raspberry Pi books. Just take the official one. It's really good. It's got really simple examples, lots of pretty pictures, and it's very straightforward. It'll get you going from nothing to semi-expert. So this being Linux, there isn't a sort of apt-get install .NET 5. There is actually quite a few steps you have to go through to install .NET on Raspbian. Fortunately, Pete Gallagher of Nottingham has written a nice bash script, so you just run the bash script and it runs it all out for you. Some people install VS Code on the device for editing. I don't do that. I have Visual Studio on my PC, and then I SFTP over it onto the device. and it's all secure by default, so everything's switched off. So you need to pay attention to these security settings. So when you log into the desktop for the first time, you get the Hello to Raspberry Pi screen like this, and it's got a menu system like you'd expect. And if you go down here, Preferences, Raspberry Pi Configuration, and Configure, it says all of these will be switched off by default. So the camera, you can't SSH to it or use the SPI I2C interfaces. So you need to switch on at least a few of those so you can get going with it. So that's typically what I have. Oh, I2C is usually on as well. So now we're going to talk about controlling the things. So digital input and output. So digital means zeros or ones. Is something on or is something off? Analog input, is it slightly on? Is it more on than it was before? Something called pulsed wave modulation, I2C, which is where the whole world sort of expands and you can control all sorts of interesting things, and a camera, which is quite useful from time to time. So you'll be spending a lot of time in this namespace here, device.gpio, and the device bindings. So GPIO is sort of the basic on-off stuff, and the device bindings is when you have really more complicated, complex devices that people have written interfaces into. And it's all open source, and you can look at that URL. So this is where the action takes place, the general purpose I/O pins, and they all do different things. So you've got two 5-volt power supplies, 3.5 volt power, loads of general purpose I/O. So these are pins that are configurable to either be on or off, and you can turn things on or listen to signals that are coming in. Loads of grounds. I don't know why it's got so many grounds, but there you go. So the hello world of embedded devices is to flash an LED. So here we've got an LED connected to an output pin. You've got a current limiting resistor to make sure you don't blow the LED, and then it all goes back to ground. So if you focus in on that, it looks like that. So the code to do that is setting up a general purpose I/O controller, open the pin, set it to be an output, and then do a continuous loop, write to high, wait a bit, write low, and then it outputs like that. And that's the hello world of IoT. All making sense so far? Great. So now LEDs are all right, but you want to control a few more interesting things. So these can all be run off the GPIO ports. You've got an LED, you've got a buzzer. This is an infrared LED. You can actually fire a small laser if you're into attacking people. You can control a relay, so that's controlling high-powered devices like your kettle if it's rated high enough, and a multicolored LED, for instance. So they're all examples of different outputs you can control. So you as a developer, you write your code and it sits within your computer, and you can call APIs and do all those funky things, but this is how your code can actually reach out into the outside world and control more interesting things. So as an aside to electronics, as I said, I'm not an electronics expert. I find some of the electronics a bit hairy. So there is this recipes site you can go to, written for Raspberry Pi, where it goes, if you want to control a motor, you need a motor controller, and this is how you connect up the pins, and here is some code you run, and that's how you do it. So rather than you reinventing the wheel and working from scratch each time, someone has already done the recipes. So if, for instance, we're interested in working out how we control the servo. Oh, it doesn't give you a nice picture. But anyway, there's some code. You could use motors. 2 motors, button controlled motors. There you go. So lots of LEDs, LED character display. Oh, you've started from the wrong place. Will it work? Yes, okay. So when you think, well, I want to control an LED or a push button or a relay, you'll see a wiring diagram, and it'll talk about pull-up resistors, pull-down resistors, anti-short resistors, anti-back EMF diodes, and suddenly your head explodes and you think, oh, hang on, what kind of worms am I opening here? So what I propose, for instance, they're controlling the relay. You've got an LED that shows it's on, you need this resistor, there's a transistor here, and there's a back EMF diode. But all of that is packaged on that control there. And you can buy a big pack of these controls. So this is a moisture sensor, this can read a memory card, that's a temperature humidity sensor, and it's all packaged with all of the peripheral components around it, so you don't have to bother with all of that electronics, it's just done for you. And if you're interested, there is a selection of them you can look at here. It's called the Geekcrete 45-in-1 sensor module starter packs. So if you get it from Banggood for about 15 quid. So it's really easy to connect. It's just like you connect the device and the pin here to the output, and then do this little bit of code, and it's all working, and you don't have to bother with interfacing. I will be sharing the slides and GitHub and everything else after the presentation. And then there's another document which is a description of how to use all of those devices. So of course we want to control the things, and we do that with Azure IoT Hub. So it's free for less than 8,000 messages a day, so that's easily enough for this demonstration, and a lot more. You can control hundreds of devices. I've got one device. It's backed by a commercial scale event hub. So I will be demonstrating how I send messages from my phone to the device and back again via a number of different standards. So I'm using AQMP, but it can also use HTTP and MQTT. It's got a concept of device twins, so you send it a JSON blob and it goes, I want my device to be configured like that. And it picks through the blob when it receives it, and then you can respond to that as an event and then turn things on and off. So the setup is really trivial. It's so trivial I'm not going to go through it, but basically you need a name, you need a device for the name, and then you set up what's called a direct method. So I've set up an IoT hub and a device called Raspberry Pi 4 in the IoT hub. So you got this useful tool called the Azure IoT Explorer, and my direct method is called control action. And then I've created this bit of JSON here, which I'm going to send down to it. So it says set relay number 3 value 1, which is on, and then it says this turns the light on. So I just click invoke. So there you go. If you can't see at the back, the light has switched on. And if I change that to 0, switch it off again. So what is happening there is the IoT Explorer is talking to the data center where my IoT hub is in Cardiff. And this, when it switches on, subscribes to events from that. So the message gets pushed down to that. And then I've got code which is running on the Pi, which understands that JSON and then performs actions. And of course, later on we'll see how it works the other way as well. So the code's really simple. So this is on the Pi. So I'm creating a device client. I create it from a connection string. So when I create the IoT hub and the device in Azure, it gives me a connection string. So I just need to pop that in my code somehow. And then set the method handler. So that's control action, which I displayed, showed you. And then I'm pulling out the JSON, deserializing it into my object, and then performing actions based on it. So what's the development experience like for C# and Raspberry Pi? So I do all my development in Visual Studio, and then I publish to a directory. Some people use Visual Studio Code on the device. I've just chosen not to do that. The key bit of config you need is when you publish, it has to be target runtime, Linux ARM, target framework, .NET 5. If you get that bit of config right, then it will actually run. Otherwise, you're pushing a .NET executable to a Linux system, and it's just never going to work. Fixed IP helps because you can FTP. And then I tend to, once I publish to a directory, I SFTP the files onto the Raspberry Pi because I've configured the Raspberry Pi to allow SFTP connections. And then you need to set permissions because once it's on the Pi, it doesn't have permission to execute. So you have to do chown user. So for instance, chown pi/control. My executable is called control, and chmod control. And then I execute it using /control. And away you go. So inputs. So these are the things you can listen to. So we'll see later how we can get those events back to a listening device, such as my phone. You've got a push button, so you can respond to someone pushing things. There is one on the board, I'll demonstrate later. A read switch, so if you've got an alarm system at home and you open the door or open a window, you will have a read switch in there with a magnet next to it, and when the magnet moves away, it breaks the switch, and when you put it back in, it opens it again. That's a Hall effect transistor, so that detects magnetism. Got a tilt switch, a ball switch, and a knock sensor, so they all detect different kinds of orientation of your device. An infrared sensor, so there's a transmitter on one side and a receiver on the other, and if you block it, it makes a circuit or otherwise. Infrared receiver to match the infrared transmitter we saw in the previous slide, and there's a motion sensor. So again, with the alarm system, if you've got a PIR in your system, in your house, that's roughly like what it does. It detects changes in heat. So the next interface I want to talk to you about tonight is PWM, or pulsed width modulation. So degrees of onness or offness. So for instance, this is a 0% duty cycle, or 0% on, and then this is on 25% of the time, 50% of the time, and 75% of the time. So it's sending pulses out of a pin, and then the devices that listen to that are designed to understand what to do with that pulse and different duty cycles. So this is 100% and it's all on. So for instance, here you can see the pulse is increasing between 0 and 2 milliseconds, and a servo is registered to either be fully closed or fully open. Here you've got an LED that's controlled in the same way, varying between 0 and 100%. Okay. I will now do a demo. So on this demo board, we've got a variety of different devices. So if you can see at the back, you've got what's called a continuous servo. So rather than this being an arm that sweeps from one side to the other, as you increase the pulse or decrease the pulse, it changes the velocity at which the wheel is spinning. So this is good for controlling like small robot wheels. And here you've got a pan tilt mechanism. So here it's rotating and then rotating back. But basically you've got two stacked servos in there. Oh, I picked the wrong one. See if we can find something new. Yes, thank you. That one didn't work. Okay. Oh yeah, there he goes. So that's the tilt. He was doing the pan before. So So all that's doing is calling direct method on my device by sending a JSON packet down to it. Okay. Just going to show you something I forgot to show you before. So an output. Okay, so it's very simple. So you've got a multi-LED here with some attached to some current limiting resistors here, and it goes back to the GPIO. So for those at the back, there's actually an LED going red, green, blue, white, red, green, blue, white. We can control the things here. Okay, so that's outputs and PWM. Did all that make sense? Good. So those are the pins. So it's got two native hardware PWMs, and you just configure them in code as to which you want to do, and plug in into the board. So the kind of things you control with PWM: servos, as we've seen on the deck, lamps or an LED partially on or partially off, pumps, motors, fan speeds, this display dial, so something that's partially on or partially off, and audio effects. So here someone's got a buzzer and PWM, and he's actually got the Star Wars theme tune as of PWM example, which is quite fun. And the speaker, lots more. So that's the wiring. You need positive, negative, and a signal into one of the hardware PWM pins. So very simple to set up. You say, I define an object called servo, which is in the software PWM channel. It's on pin 18, it has 400 hertz, and the duty cycle is 90% to start with, and then you can vary the duty cycle between 0 and 100 afterwards. Hardware pin, you can do software, but with Raspberry Pi not being a real-time operating system, I find that it tends to stutter a fair amount, so I prefer the hardware PWM if you can use it. So software is just basically the operating system varying what goes over the output pins, whereas and if something else is running on the board at the same time, it can interfere with that cycle. So if it's a sensitive device, it stutters. So there you go, a servo arm and a pan tilt. Cool. So I2C. So once you discover I2C, everything looks like an I2C interface, because this is where you can get some really interesting hardware and start controlling some interesting things. You've got two native I2C ports. The thing is, you can. I'm only using two, even though I've got about 8 I2C devices on there, because you can just daisy chain them together, because it says I'm sending a signal to this device and I want it to do this, and only that device listens to whatever it is you want to do. It's two-wire communication, short range, so it's less than a meter. If you do more than that, then you start getting capacitive effects on the wires and it doesn't behave like you'd want it to. There's some really good I2C tools which really help you, because you can tell whether devices are attached and have been discovered or not, because sometimes they don't work. So I2C tool, apt-get install I2C tools, and then use I2C detect, and it'll tell you which ports are occupied and which are not. Yeah, you've got lots of different things you can do here. So relay controller, so this is my relay hat. So that's for controlling large voltages and large currents. PWM controller, so I was actually cheating earlier, so I can control up to 16 different PWM devices here using I2C. Digital I/O expansion, so if there aren't enough I/O ports there, I can control even more by using the I2C interface into them. Got an LCD screen here, it says Pi control started, for those who can't see at the back. Yeah, you need to be in front of it. Analog inputs, so there's a analog to digital converter which will communicate via I2C. RFID tag, rotary encoder, basically a volume switch. It's also got a BME 280, which is a temperature, pressure, humidity sensor, accelerometer, EPROM, the list goes on and on and on of things that take an I2C interface. So life starts getting exciting. So a bit about prototyping. So once you start putting these things together, as you can see, I mean, this is quite an organized mess, but without some thought about how it's all going to fit together and be contained, it really does become a bit unwieldy, particularly when you chuck something like that in the back of my car and all the wires have the potential to pop out on the journey down from Leeds. So you need some decent cabling. So this is male to female, so this will attach things, and that's female to female. So a Raspberry Pi to an I2C board, for instance. All of these are DIN rail mounted. So this is a DIN rail. So I buy devices that are specifically DIN rail mounted, like these connector blocks here and the transformer and the backing to the Raspberry Pi. That holds it all in one place, so it doesn't flop about all over the place. Connector blocks, so they can take hundreds of amps across them and just neaten up the wires and stop them becoming detached. A breadboard for rapid prototyping. So there is a breadboard that's on this DIN rail down here. So what happens here is if you put a wire in here, it's connected all the way along that rack here, and if you put a wire in there, it's connected along there. So you can have that as a common positive and that as a negative and put your components across here. And then I use something called Totemaker, which is posh man's Lego because it's very expensive, this stuff, but it's very flexible, and mount components onto it, like the servos and all of these I2C devices, so that they stop flopping about all over the place. So think as your system gets bigger, think about prototyping and how it's all going to be managed. So as an example, we've seen PWM controllers. This is something called a PCA 9685. So when you connect it to the Raspberry Pi, you need a positive and negative, and the two I2C clock and data pins connected. And then because of that, you can then control up to 16 different I2C devices. So because this takes a lot of current, you've got a separate power supply here, and that goes straight to the transformer. So you can control as many devices as you want. Code is really simple because someone's written abstraction for you. So I just say, well, I want a PCA 9685 driver, set it back to base, and then for each driver and channel, I set the duty cycle on it. So, and as an aside, choosing hardware. So you can go onto the Pimoroni website, which is a thing of beauty, and there is a cornucopia of lovely components that will make your mouth water. They are so beautiful. I mean, just look at that ink screen, static ink screen. Ladies, come. Yeah.
Right here in Sheffield. And they're right here in Sheffield.
And they are right in here in Sheffield, so you're supporting a local industry. So yeah, you've got all these beautiful things you can control with your Raspberry Pi, and you go click buy, and then they arrive. And because you're in Sheffield, you don't have to wait too long.
They do. You can arrange a local pickup if you want.
Oh, right. Are they really local?
Yeah.
Oh, okay. Yeah.
It used to be just down, literally just down the road.
Oh, okay.
Yeah, they used to be a lot more local, didn't they?
Yeah. It used to be a lot more local.
So unfortunately, there is bad news. So there is what Pimoroni stock, and there is what you can use. And these two things are not the same. Okay? So I would advise caution before pressing the purchase button. So, just to explore that a bit. So if you're using .NET, for instance, then people haven't written wrappers for everything. So if you want an analog to digital converter, there are some examples that people have written wrappers for. You want an accelerometer, a gas sensor, liquid sensor, barometer, altimeter, thermometer, gyroscope. You know, there are lots of different things you can use here. But if you go onto the Pimoroni website and you go onto the component, it'll go right at the end, they'll say, and the Python library for this is here. Or, so if it's been written for Raspberry Pi, there's usually a Python library. If it's written for Arduino, there's usually a C library. And then occasionally there is a .NET library. And then if you go to that namespace in IoT source devices, people have written wrappers. So that's what I did. I got all googly-eyed when I first started out on this adventure, and I bought the Relay hat, which has a Python library but no C# library. So it was pretty straightforward to go on a website and then go and then translate it into C#. So getting a Python to C#, pretty straightforward. Getting C to C# is a lot more complicated because there is no straightforward way of transpiling C to C#. Now, because it's I2C, it uses all of these bitwise operators, which I don't really understand, but you don't need to understand because someone's written the code in Python, which you can then translate. So, yeah, it's doable, but I would recommend looking at Pimoroni, looking at what people have got drivers for, and then the Venn diagram of the two is your happy space. Cool. So we want to control higher power devices and need something called relay. So relay is an electromagnet next to a bar, and when you put a current across it, the bar swings across and closes a switch. Depending on which relays you've got, these are rated to 10 amps. So I could run an electric fire off this through my Raspberry Pi if I wanted to. So I've got a couple of high power devices here. If I can remember which ports they're on. Okay, so there's a light that's come out of my kitchen. So a light's gone on there, so that's about 0.5 amp. And if you can hear, there's a slight click in the air. That's the relay flicking on and then flicking off. And here, wrong one. I've got a solenoid. So solenoid is basically turns of wire around a metal tube. When the wire is charged, creates a magnetic pulse, and the iron bar swings through. And then when I remove the current, it drops back again. Yeah, and I do have a presentation with fireworks, but people of nervous position don't announce they have nervous position, so I got told not to do that part of the presentation. Alas, alas, I know. Yeah, and there is, you can see the bar swinging backwards and forwards there. And that's how you control the relay board. So yeah, typing's not very pleasant, but it gets the job done. So I'm going to have a little diversion into the world of Blazor, which is a single-page application framework. So I've done server-side Blazor, and I've chosen that because it does push updates using SignalR. So I don't have to bother with all the mechanics of SignalR. I've got a web page, and if the web page updates, it knows to update the device, and I don't have to do all of the plumbing to make that happen. Blazor does it for me. So for instance, I've got a form control here called get input, and then it goes away and gets a value, and then it changes a property in the background, which is a text field, and then it sets at the bottom get input value is high. So this is attached to a method, this is attached to a property in the code behind in the form, as is the output. So that's how the sort of model works. and you wire it up like that. So you create a button in HTML, and then you've got an on-click event. Mine's called send message, so I've got some code behind that responds to a message. And here I've got a text field, so that has its class and message set by some code in the background. So for instance, if I catch an exception, I say message an exception occurred and change the color. So when I push the button, signal R carries a message to the back end and does stuff. And equally, when there's a change in the back end, it pushes those updates down to whatever is looking at the page, like my mobile phone you've been seeing me play with. So how you set that up on the website is you create a service client from a connection string. So when you set up the IoT Hub, you get a couple of connection strings, one for the device, one for the service. So the service would run on a web server and say, I want to set up a device method. Here it is, control action in my case. Serialize my payload to that, set the payload, and then invoke the device. So when I push a button on here, it invokes a direct method, as you saw me do with the IoT Explorer. Okay. So here I've got. You can see the LEDs are cycling here. So just talk through what's happening there. So I press a button, signal R transmits that to the data center in Cardiff. When the application starts up, it connects to IoT Hub. It then sends a message to the IoT Hub. When this device starts up, it sets up a persistent connection to the data center. When a new message is received, it then takes that and then invokes the direct method. So then it changes the LED settings. What was I doing? Yeah. Okay, any questions on that? Cool, right. Oh, that didn't work. There you go. Straightforward. So now your device is living and you can control it from wherever you want. Quick aside on the camera, you get three types of camera: normal, high def, and infrared, and you just attach it to, the port is under there. It's like a strip cable. All you've got to do is get the strip cable the right way up and it'll work. And it's very simple to catch that an image as a blob using code. There you go, there's the interfacing. So now a digital input example. So here we have a current limiting resistor to stop, because what you're essentially doing is shorting that. So there's a 5-volt power going there to an input pin. And you define the input, the pin as an input, and then the resistor just stops it making a short across. There you go. So all of the yellow ones are any ones you can set as inputs. The code's straightforward, so you need a controller. Then open the pin and set it as an input, and then read the value out of that. Right, so I'm just going to see if this works. Right. Can you see this where it says message from device? Button's value is false, true, false, true, false. So there's no interrupt system on the Raspberry Pi. What I've got is code that says, did the button state change? Did it change? Did it change? Every quarter of a second. And when it did, it sends a message up to IoT Hub, and then my website is subscribing to changes from IoT Hub, and then my device, my web page here on my browser is subscribing to those updates via SignalR. So you can see that's going all the way to Cardiff and back again in fractions of a second, so it's pretty responsive. Now you can have analog inputs. So this is stuff that's not zeros or ones. So potentiometer, this is a potentiometer here. So like a volume control, you can also have a thermistor, which is a temperature sensor, pressure sensor, force sensitive resistor, distance sensor, basically things that provide an output, an input to you that's between 0 and 1. Sound sensor, flame sensor. Some examples of that in my component pile over there. So if you're using Arduino, you get analog inputs for free. If you're on a Raspberry Pi, you have to work a bit harder, but you know we like work. So I have a analog to digital converter here, which I talk to via I2C. So we need positive and negative, then the two I2C data pins, and then we can control up to 4 different analog devices and get inputs from them. So there's a light-dependent resistor, I think that's a magnetism sensor, and volume control. I didn't, that's why it's not working. I need to remember which. Okay, so this is connected, I think, to this volume control here. So if I twiddle it slightly, so it's gone down from 100% to 95%. 71%, I'm not turning it enough. There you go, 42%. And there's a light dependent resistor there, so I could do another demo where I hold my hand over it and it changes the value. So when you're doing analog inputs, you have to work a bit harder and use an ADS 1115 to understand the input and then interface it using I2C. But the code's pretty straightforward. So sending messages to the device, to the event hub. So this is the Raspberry Pi talking to the event hub. As we saw when I pressed the button, it sends a message. So I just get this JSON packet called device event, and then at the other end we're subscribing to those events. The event hub, Azure IoT Hub is backed by event hubs, so it's scalable to millions of events per second. It's basically Kafka as a service. You've heard of Kafka, it's sort of enterprise level messaging. LinkedIn use it amongst other people. And then receiving messages from the event hub, so they can be routed to blob storage or service bus or any number of different places. If you disable the fallback route, you can send it wherever you want. And then subscribe to those events. So this is in my Blazor site. So you need a blob storage connection string, because if you've used Kafka before, when it processes a message, it doesn't consume the message and then delete the message off, because that will be slow. What it does, it just sets increments a pointer. So, well, I've read message 100, I've read message 1,000,000, I've read message 2,000,000. So you need a blob storage container to just keep that pointer somewhere. So that's all that's for. So then you can set up a consumer group and then set up 2 event handlers. So I've got a code for processing events and processing errors. So that's called whenever a message is received from the event hub to Blazor. And there's my event handler. So I'm expecting it's going to be a UTF string, which I then deserialize to my device event. So the Raspberry Pi creates a class called device event, and then this is consuming that device event. And based on that, it'll update what's on the screen. Did all that make sense?
So you're using Event Hub and IoT Hub in this?
IoT Hub is backed by Event Hub, so you get one for free.
Okay, so you're using the IoT Hub but through an Event Hub interface to it?
Yes. Yeah,
Or class.
basically. Yeah. Okay. Yes, so we respond to a couple of events got set up here. So when the device starts, it sends a message, says, hello, I'm here. Also, it sends a message every 2 minutes to say, I'm still alive, and also what the temperature is in the room. Unfortunately, it doesn't tell us if the pizza's arrived yet. And as we've seen, button pushing, and there's a light sensor there as well. So with all this, you as developers have the power for your code to reach out into the real world. There are a number of interfaces you need to understand, like digital I/O, PWM, I2C in the camera. There are ways of making the electronics simpler and more straightforward, and the interfacing trivial. Not everything you can buy can be controlled yet, but there are ways around that. And one of the main points is Azure IoT Hub can be a really good intermediary between you and the device, so you can send messages to and get messages from it. There's a few resources, so there's a sensor pack, a how-to book, and a really good starter kit. So Pi Moroni is good, but unfortunately the Pi Hut has the edge. Sorry, Sheffield. So yeah, I'll share all this on the Meetup website as well. But there you go. There's code, there's the slides, and if you want to connect with me on LinkedIn or on Twitter, feel free. Any questions? Thank you. Thank you.